So let us recall what we had done last time. We have started looking at integration. So given a function f on an interval a b to r, f bounded, we defined the integral of f via upper sums and lower sums. So we defined for every partition P, we defined what is the lower sum, what is the upper sum, and we said f integrable if and only or integrable definition if the supremum of least upper bounds of L lower sums is equal to greatest lower bound of upper sums, and that was denoted by integral f dx, right. So we gave some examples. F monotone implies f is integrable. Then we gave some more examples, namely the function f of x is equal to 1 if x belongs to rationals, say in 0 1, and 0 otherwise is not, because upper sum is always 1, lower sum is always 0, is not integrable. We also gave example of Thomas function, or called the popcorn function, which has, so this function has the special property, namely it has infinite number of discontinuities. In fact, these discontinuities are all rational points. In every subinterval of 0 1, but is integrable, right. So there is various examples of integrable functions, keeping in mind the number of discontinuities the function can have. So as we were pointing out that this function is discontinuous everywhere. Monotone is discontinuous at all rational countable, at the most countably many, and Thomas function has infinite number of discontinuities in every subinterval and is integrable. So let us prove an important class of functions which is integrable, namely, so theorem, let f be a b to r, f continuous. So let f be a continuous function on an interval, closed bounded interval a b, then f is integrable. So let us prove that. So basically what we want to show, it is integrable. We are not interested in computing the integral. So we will use a criteria that given any epsilon, so we will use a criteria that for every epsilon bigger than 0 there exists a partition P of AB such that upper sum minus the lower sum is less than epsilon. So this is will show. So this is what we will show, and we had observed that this is a necessary and sufficient condition for a function to be Riemann integrable. So let us start with an epsilon. So fix. So what does continuity imply? F continuous implies two things. One, F is bounded, right? In fact, it attains maxima, minima, we know that. And second, we proved that F is uniformly continuous. Every continuous function on a closed bounded interval is uniformly continuous. So what does uniform continuity say? So hence, we are already given an epsilon, so given epsilon, so for epsilon but 0, there is a delta such that whenever x minus y is less than delta, that implies fx minus fy is less than epsilon. Whenever 2 points are close, their values are close. That is what uniform continuity says. So mathematically that says that for any epsilon bigger than 0, there is a delta, so that whenever x and y are close by a distance delta, the values are close by epsilon. So that is quite useful in the sense that now we can select a partition so that the points are always inside a distance delta. So choose a partition, so let P be a partition of AB such that so it divides into subintervals, so such that, okay, I did not introduce this notion is less than delta. So what is the norm of the partition? Norm of P, a partition, is defined as the maximum maximum of the length of subintervals. So xi minus 1, I between 1 and n, if P is the partition say a equal to x0 less than x1 less than xn equal to b. This is a definition of length, definition of the norm of a partition. So every partition divides the interval AB into subintervals. So look at the maximum length of the subintervals, right? And that maximum length is called the norm. So this is what is called. So this norm, this is called the norm of the partition. So uniform continuity says given epsilon there is a delta, say that whenever 2 points are close, fx minus fy is close. So if we choose a partition whose maximum, whose norm is less than delta, then that will mean that for any 2 points in a subinterval, right, the length will be less than, the distance will be less than delta, and hence the values will be close by epsilon, right. So now also observe, also note f attains maximum and minimum on each subinterval, right, because it is continuous function. So let capital Mi, which is the maximum of f of x, be attained at some point. So let us call it as x belonging to xi minus 1 to xi. Let us say this value is attained at some point, say xi dash, okay, and where xi dash is a point in between and small mi is the infimum of fx, x belonging to xi minus 1 to xi, and let that be attained at some point, say xi double dash, where xi dash and xi double dash belong to, right? So it is saying that f is a continuous function. So look at its restriction on the closed bounded interval xi minus 1 to xi. It must have a maximum value somewhere in that interval, it should have a minimum value in that interval and must be attained. So those points we are calling as this. So why we are doing all that is because now let us look at the upper sum. Now upper sum with respect to s minus the lower sum with respect to f. So what is that? So that is equal to capital Mi minus small mi 1 to n, maximum minus the minimum, right, into the length of the interval xi minus 1, right. Now this value is taken at that point, so this is I equal to 1 to n, so f of xi dash minus f of xi double dash into the length of the interval, right. So that was and now these 2 points xi dash and xi double dash are inside this interval, right, and so that means the distance between them is less than delta, because norm of the partition P is less than delta, and whenever that happens we know that by uniform continuity these values are small. So that is all the reason we did that. So let us imply, so this is less than or equal to delta times sigma I equal to 1 to less than delta, so this is less than epsilon times xi minus 1, because xi dash, xi double dash both belong to the interval xi minus 1 to xi, implying that the distance between them is less than delta, and that should be okay to say that, implying that f of xi dash minus f of xi double dash is less than epsilon, right, by uniform continuity. So what we have done is the interval AB, we have found a partition such that the distance between any 2 points in the subinterval is less than delta, and that delta is corresponding to the uniform continuity of the function. So the values for any 2 points will be less than epsilon. So all that is used to bring it here. So what is this quantity? So consecutive terms will cancel out, so this is epsilon times b minus a, right. So given epsilon bigger than 0, we have found a partition P say that the upper sum minus the lower sum is less than epsilon times b minus a. So the constant times something does not matter, we could have started with epsilon divided by b minus a, right. So hence f is integrable. So that proves the theorem that every continuous function is integrable. Actually, historically, this was first proved by Cauchy. You will find Cauchy coming in your various courses. He was a French mathematician who contributed a lot of things in a lot of branches in mathematics: real analysis, complex analysis, algebra, statistics. You will have Cauchy's distribution coming in statistics and probability. So, and he was the first one who proved this theorem. gave a proof that every continuous function. In fact, he was the one who actually defined rigorously what is the notion of what is the notion of a function being integrable. Okay, and he at that was the time when mathematicians did not bother much about continuity or discontinuity. They thought every function is continuous, kind of a thing. So he assumed not only continuity, he even assumed the fact that we are using that it is uniformly continuous. So that was the only I won't say mistake, but that is oversight, that what we call now as uniform continuity, he thought that is continuity at that time, and he gave a rigorous proof of this. Right. So the class of integrable functions is quite large. It includes all continuous functions on the interval AB. Okay. Right. Now the problem is okay. So this is we had started looking at the two questions, that what is the class of integrable functions. So we have given a lot of examples, and now second problem is how does one compute integral. So let us answer that question. How does compute f dx a to b? Can we have a way of computing for a given function what is that integral, right? So there comes a theorem which is very important, and that's why this integral becomes important. That is called the fundamental theorem of calculus. So let us state and prove what is called fundamental theorem of calculus. So theorem. So let me call this as part 1. There are two parts of this. So let us. So it says let f and capital F be two functions defined on the interval AB to R with the following properties. 1. F is integrable on AB. Capital F is continuous on at least the open interval AB, and F is differentiable with continuous in the closed interval. I am sorry, we should say F is continuous in the closed interval and is differentiable at least in the open interval, and differentiable capital F is continuous and differentiable in interval AB such that its derivative is the function f of x. So small f and capital F are related with each other in the following way, that the derivative of capital F is equal to small f in the interval open interval AB, and of course we are putting conditions like small f is integrable, capital F is continuous on the interval AB, so it will be integrable. Then if all these conditions are satisfied, then fb minus f of a is equal to integral a to b fx dx. So the function capital F and small f are related with each other by this equation, that if small f is the derivative, so look at this. So this integral, if small f is the derivative of capital F, then integral of small f is just fb minus f of a. That means what? there is a big advantage that for a given function, if you are able to find that it is a derivative of something, then integral of that function is just fb minus f of a. You don't have to go to partitions, you don't have to go to limits or anything, right? So this is and this was again proved by Cauchy rigorously, and historically it was a very significant theorem. At least it relates differentiable functions derivative with the integral. So in that sense, people started looking at derivative as and integral as the processes of reverse of each other kind of thing. There is a reason because of this theorem. But the importance of this theorem lies in the fact that it helps you to compute integrals, right, if you are able to recognize, right, that small f is the derivative of a function capital F, then the integral is. So let us prove this theorem, give a proof. So we want to compute f of b minus f of a, and we know what is f of b minus f of a, and we want to show it is the integral, right? So essentially that means okay, doesn't matter. Yeah, so that means essentially that this is a number we should be trying to show lies between the upper and the lower sum. Whatever be the partition, we can show that for every partition P of the interval AB, right, fb minus f of a is in between, then that must be the integral, right? So that is what we are trying to show. So we will show for every partition P of AB, lower sum is less than or equal to fb minus f of a is less than or equal to the upper sum. Right? Or that is enough to show that, because if this is the only number between upper and lower, they are shrinking, so this number must be equal to the integral of the function. So let us start with a partition. So let P be a partition, and so let us say A equal to x0, xn equal to b, be any partition of AB. So now let us you see what we are trying to do is, I want to bring in inside the upper and the lower sums. So I have to go to the upper and the lower sums with respect to the partition P, right? Somehow I have to steer my arguments towards that idea. I should bring in this. So now look at fb minus f of a. This is what we want to compute. And now here, this is how the partition comes in. This is same as f of xi minus f of xi minus 1 I equal to 1 to n. Yeah, that's okay. No, it's okay. I add and subtract the consecutive values of f at the consecutive points. See, so now partition points are inside now, right? So let us call this as 1. Now what is, now the next step should be that this partition, this f of xi minus f of xi minus 1 should be related with small f, right? Then you will get some summation kind of a thing in terms of small f. Now, so, and small f is the derivative of capital F. So what is the, which is the theorem which relates a function with the values of the derivative, right? So that is how one thinks about. So fb minus f of a in terms of the derivative, and that is Lagrange's mean value theorem. So by Lagrange's mean value theorem on xi minus 1 to xi. There is a point ci belonging to xi minus 1 to xi such that f dash at ci is equal to f at xi minus 1, sorry, f at xi minus f at xi minus 1 divided by xi minus 1 for every I, right. So once that is the case, that means what? So that implies that f of xi minus f of xi minus 1 is equal to f dash of ci at and the length of the interval. So that is Lagrange's mean value theorem essentially. You see how Lagrange's mean value theorem is playing a part at all these places. And this derivative of small f, capital F is small f. So it is f of ci xi minus xi minus 1. Right? Now keep in mind, I said apply Lagrange's mean value theorem on this interval. One should check the conditions of Lagrange's mean value theorem are applicable. Capital F is continuous everywhere. So it is continuous on the interval xi minus 1 to xi. It is differentiable in the open interval, right. So it will be differentiable in the open intervals xi minus 1 to xi, each one of them. So Lagrange's mean value theorem is applicable for each closed bounded interval xi minus 1 to xi. So that's why those theorems were, those conditions were put, both of these ones, okay. And now, so we want to go to 1, we need summation. So implies summation of xi minus f of xi minus 1 equal to 1 to n is equal to sigma f of ci I equal to 1 to n xi minus 1, right, and that by 1 is equal to fb minus f of a. So let us call this as 2. Okay. So what we have done is we have computed fb minus f of a in terms of the function small f. It says this summation is equal to f at some point ci. Ci is a point in that interval into the length of the interval, right. So okay. Now what is f of ci? That is the value of the function at the point ci, right. So it will be always bigger than or equal to the minimum value and less than or equal to the maximum value. So using that implies that if I look at the minimum value small mi xi minus 1 will be less than or equal to summation f of ci. So okay, this is not imply note, this is the observation minus xi minus 1 equal to 1 to n, and that is less than or equal to capital M. Capital M, I have put summation, so let me put summation everywhere, right, less than or equal to, I put summation in between, so less than or equal to summation capital Mi of xi minus 1. Is that okay? Because this is a value at some point in between in the interval. So f of small f of ci is bigger than mi, is less than capital Mi, right. So now just combine. What is that in between quantity? 1 and 2 say that is fb minus f of a. So 1 plus 2 plus you can call it as 3 if you like, imply that so this is a lower sum is less than or equal to fb minus f of a is less than or equal to the upper sum, right, because this thing is a lower sum left hand side. In 3, this is lower sum, this is the upper sum. So lower sum is less than this summation, and that summation is by 2 equal to sigma of capital Fi, and that by 1 is Fb minus f of a. So putting these 3 equations together, we get this, and that completes the proof. Right? So this is one of the important theorems in integral or in the whole of calculus or analysis as far as differentiation and integrations are concerned. It relates differentiation and integration in the way that if you know that the derivative of a function, then you can compute the integral of that function. So as a consequence of this, all you get every derivative formula gives you an integral formula. Derivative of sine is cos, so if we integrate cos, we must get back sine. So integral of, right, derivative of any function, any derivative formula will give you a corresponding, and that's one of the reasons that as soon as differentiation is done in undergraduate courses and integration is started, immediately 500 formulas appear, okay, and you are sort of supposed to remember them and start computing integrals. Okay? The culprit is fundamental theorem of calculus. Okay? And historically this was very important because not only it said that for every continuous function you can have the integral, right, and if you know that this function is the derivative of something, then you can compute the integral, and that led to a lot of research in what is called theory of Fourier series. So it gets related historically with the theory of Fourier series. Okay, right. So let me not go into that. So basically the important thing is, as far as computation is concerned, so this is what is important. You can compute integral of f if we know that, and keep in mind f dash is equal to small f, so automatically says small f is continuous because capital F is continuous, right? Small f is differentiable. Okay, right.